Okay, so greetings from Bill Industrial and Technological Museum, BITM, Kolkata, a premier institute under NCSF, Ministry of Culture, Government of India. So we welcome you for inauguration of BITM Astronomy Club. So greetings from Bill and this is a club which will be held monthly, once for school student and once for college student, and today is day of inauguration. And astronomy, as you know, it's an important part of society due to both tangible and intangible reasons, and implication on basic science, technology, noise transfer being the most important contribution. Probably the most important contribution is the fact that astronomy provides us the awareness of how we fit into the vast universe, as American astronomer Carl Sagan has portrayed in Astronomy, simplest but most inspirational contribution to the society in his book, The Pale Blue Dot. It has been said that astronomy is a humbling and character building experience. So there is perhaps no better demonstration of the folly of human conceit than this distance image of our teeny world. So uh, today in this inauguration occasion, we got Professor Nandi as our guest speaker. So first we'll start with a welcome note by our director V.S. Ramachandran. So over to you, sir.
Dear Astronomy Club members, online viewers, I am extremely happy to have Professor Dibyendu Nandi, a very distinguished astronomer and Professor, Center of Excellence of Indian Institute of Science Education and Research, Calcutta, to be with us during this auspicious occasion, that is inauguration of our Astronomy Club. Sir, this was planned more than 2 years back because of Corona. We were forced to delay it. And then I'm very happy now it has started. And that it is started by one of your students, Dr. Rakesh Majumdar. Recently he joined us as curator. And the moment he joined, I was very happy that immediately I told him start an astronomy club. Because I have got a great experience with the astronomy club in Calicut. A brief introduction about the speaker of today, Professor Nandi. Professor Nandi has got an excellent academic track record. He is a PhD holder from IISc Bangalore, the prestigious Indian Institute of Science, Bangalore. He completed in 2003, and then 2 years he did postdoctoral also in Montana State University for 2 years. And he is currently in many prestigious national and international positions like chair of the Astronomical Society of India, Public Outreach Education Committee, various committees he is there. In his research career, he published numerous publications, including high-impact journals like Nature and Science. He has prestigious awards, including Ramanujan Fellowship Award, DST, Government of India, in 2008, Karen Harvey Prize of American Astronomical Society Society also. Then he has got Solar Physics Division in 2012. He is a leading role in upcoming Aditya L1 Mission. Aditya is a very prestigious project of ISRO, and he is playing a leading role in that. I am very happy to have such a distinguished speaker. Welcome you, sir. The floor is yours. On behalf of Birla Industrial and Technological Museum, I wholeheartedly welcome you, sir. Thanks a lot.
Thank you, Sri Ramachandran. I hope you can hear me.
Oh, sure.
It's a pleasure to be here. I know that we had communicated earlier and I was supposed to speak. Earlier somehow didn't work out because of the pandemic.
Yeah.
But there cannot be a better occasion than this. I'm very happy to be here formally in the inauguration of your astronomy club. Particularly happy that my former student Rakesh Majumdar, who's now associated with you, is leading this initiative. So I wish Rakesh and BITM all the best. And I hope that this astronomy club at BITM becomes a center for the amateur astronomy enthusiasts of the whole city of Kolkata to come together and share in the discovery and experience of astronomy, which is one of the oldest and the easiest access to sciences that we have. We look up and there is inspiration for all of us. Although we are losing it in the city with the light pollution, I hope that some of you sometimes take the opportunity to go out and experience the night sky. So I thought today, in this occasion, I will speak about the story of our star, the sun. I wanted to speak about the sun because I want to bring home the point to you that we do not exist in isolation from the stars and the planets and the universe that seem to be very distant and beyond us. But rather, our lives are very intimately tied to the life of the universe and the star. And not many of us appreciate that while we go through our daily lives. I wanted to bring this point home to you, and I hope that I will achieve this by the end of this lecture. So I will share my screen, and I'm sorry that I cannot be with you physically today. I was out and then I on travel, and then I contracted COVID. I'm recovering. I'm completely recovered now, but I just wanted to be safe and wanted all of you to be safe, and therefore I'm giving this lecture online. Let me just share the screen. Okay, I hope you can see my screen now.
Yes.
So I'm going to speak about the story of our star, the sun. I come from ISER, Kolkata, the Indian Institute of Science, Education and Research, Kolkata, which is an institute about 60 kilometers north of the city. And I am a physicist attached to the Department of Physical Sciences. I also lead the Center of Excellence in Space Sciences there, which is a center that was established by the Ministry of Education. So we have integrated BSMS programs, master's program, integrate PhD program for people after the bachelor's degree, and a PhD program for people who want to join us after the master's degree. You can find more details about our institute and our center in these websites, and feel free to write to me in case you have any questions in terms of pursuing astronomy or physics as a career. And you can find more details about our programs and applications, procedures for applying in the websites here. So our idea of space, that is the textbook idea, is that the space is a vast empty space where there is no changes. Nothing can in fact be further from the truth, although it's true that space is almost near vacuum, has much lower density than the density of the Earth's atmosphere. It's a changing environment. It's changing environment primarily because our star, the sun, has activity which influences the conditions or the environment of near Earth space. And these conditions change, sometimes rapidly, sometimes slowly, again governed by the activity of the sun. What you see here is actual observations of disturbances or density perturbations moving through the inner part of the solar system, starting from the sun, which is at the center, through the Earth orbit. The Earth is here, the orbit of the Earth is here as a cartoon, but the rest of it is not a cartoon. The rest of it is actual observations, which has been taken by the UT radio telescope. And what these observations show are this density fluctuations that happen because of certain activities that is originating in the center at the sun of the solar system and then propagating outwards. These are plasma disturbances, which are essentially related to solar storms. I'll be talking about that in greater detail. But also, what we know today is that the light from the sun, or the photons that are coming in, that sustain life, that sustain photosynthesis, are also variable. Sometimes the photons can be more energetic. There can be X-ray photons, extreme ultraviolet photons, related to solar storms known as flares, which again propagate through interplanetary space and can impact planetary atmospheres and our technologies. So in fact, just like there is weather on Earth, there is weather in space, and we share this changing environment or changing ecosystem, as I will try to convince you. And this is intimately connected with the possibility of life in planets and in fact our own lives. Let me now go back and begin this story right in the beginning and give you a brief history of the universe and the birth of stars. So we know that in the very beginning, there was what is known as the Big Bang. So the universe began in a Big Bang where from a discontinuous, very dense, very high temperature region, the universe started expanding very rapidly in a phase which is known as inflation. So the universe was a hot soup of various fundamental particles, but the particles that you're more aware of today, like electrons, protons, neutrons, which are the building block of the world that we see around us today, were actually formed when the universe cooled about 300,000 years after the Big Bang. After about 1 billion years of the Big Bang, eventually atoms started clumping together and forming larger and larger masses or protostars, which are the progenitors or the early form of stars which gave rise to stars like our sun. About 10 billion years into the lifetime of the universe, the first stars that formed started dying. And I will discuss what dying means for stars. But essentially, some of the stars which are very massive, when they come to the end of their life, they die spectacular deaths in massive explosions which are known as supernova explosions. And these supernova explosions essentially scattered the elements that were cooked or synthesized inside of stars into the larger part of the universe and distributed them. And it is out of these elements, through the death of the first stars, that eventually other stars and planetary systems like Earth formed. Eventually, it is those elements from the death of other stars which have found their way into our bodies and which make life possible. So let's talk a little bit about the formation of stars, right? To make stars form or planets form, you have to bring mass together. You have to somehow keep on adding atoms and produce larger masses from smaller masses, right? Now, this is typically easy to do if you're aware of gravity, because gravity is an attractive force, and gravity attracts material, and matter tends to clump together and start forming bigger and bigger objects. But then the question that arises is, why is not the universe one whole large spherical ball where matter has all clumped together? Well, so when you start clumping matter together, there are higher and higher density, and in the interior of this matter, there is very high pressure. And so while gravity attracts, pressure actually pushes, right? So collisions of these atoms, due to the high pressure and temperature in the center of accreting object, which is accreting mass, will push away the material and try to balance the gravitational attraction. When a balance between gravity, the inward force due to gravity, and the outward force due to the gradient of pressure is reached, then a stable star like the sun is born. And remember that to maintain this high pressure and high temperature in the interior of stars, some other processes are necessary. So what you see here is an image from the Hubble Space Telescope of a region when new stars are continuously forming. This diffused brown region that you see, this is a gas, this is known as interstellar gas, from where certain instabilities can start clumping the matter together. And then when matter starts clumping together, the temperature and density inside starts climbing up. Eventually, they become so high that nuclear fusion reactions are initiated. And this nuclear fusion reaction produces enough energy and a pressure gradient to hold the star against further collapse and forms a stable star. And these bright regions that you see here are newly formed stable stars. And so this is what you're seeing here is a nursery of newly forming stars. Okay, how do we form the building blocks of the materials and life that we see in the universe? Right. So the easiest thing to form is a hydrogen atom. which just has a proton and an electron moving around in orbit around the proton. Now, the universe is made up of much more complex matter, higher mass elements. How do you start forming higher mass elements? Let's take the example of helium. So from hydrogen to helium, if you go, you have to put together one more proton and two neutrons into the nuclei or the center of this atom. Now, that's a difficult job. Why is that a difficult job? Because we already have a positively charged proton in the nuclei in the center. And you have to add another proton to the system now, which is also positively charged. And you know from basic physics that when I have like charges, for example, two positive charges, they repel, right? So you have to overcome this Coulomb repulsion, these forces of repulsion, the electrostatic force of repulsion, to be able to form a higher mass nuclei for a higher mass element, for example, going from hydrogen to helium. And this requires you to overcome what is known as the Coulomb barrier, as I spoke about, which is the repulsive force between two positive charges. Now, this implies that classically, the approaching proton, the particle that is going to fuse with the nuclei, has to have a kinetic energy which is larger than the potential barrier of the two positive charges in the protons repelling each other, right? So this can only happen under very high temperature and pressure or extreme conditions that is made possible inside stars. In fact, even within stars, often this condition that the energy of the approaching proton or particle is higher than the potential barrier is not satisfied. So what occurs then within stars is a phenomenon known as quantum tunneling, which is a probabilistic phenomenon which allows this approaching proton to still tunnel through the barrier and start forming higher mass elements. So a very complicated set of physics, actually starting from very basic to various different manifestations of physics like quantum physics, plays a role in the generation of higher mass elements inside stars. And then when you are going through this process of nuclear fusion, there is a mass deficit. Not all the mass that comes in remains in the new nuclei that is formed, and this difference in mass is converted to energy following Einstein's famous equation E is equal to mc square, and that energy is released and hits up the interior of stars, and eventually this energy finds its way through radiation and convection to the outer part of a star and makes the star shine. And it is this light, the light of a shining star, like the light of a sun, which makes life possible on Earth. So I think it is important for us to realize that our life is dependent on some very intricate physics deep inside faraway stars that occur all the time. And this, when you start thinking about it, this is an amazing feeling. Okay, so after the birth of the sun, matter accretes around it in a disk and planets starts forming, and this is how planetary systems are usually formed around stars. They're captured by the gravity of the largest object, which happens to be the sun, and therefore the planets start revolving around the sun in stable orbits. Well, at least for a reasonable amount of time these orbits are stable, and in these orbits there are certain zones where the temperature and other conditions are just right enough for life to evolve and proceed. And this is how life also came to be on Earth, which is at the right distance from the sun, so that neither is it too hot, neither is it too freezing. There's the possibility of liquid water and a nice temperate climate, which is conducive towards advanced life forms. So nuclear reactions I've already talked about in the interior of stars. These nuclear reactions in the sun primarily form helium out of hydrogen, but in more massive stars, more massive than the sun, more higher mass elements are formed. The more intense is the temperature and pressure inside a star, which happens for stars much larger than the sun. You can sequentially create much more higher mass elements. And then when these stars die through a process known as supernova explosions, this death happens because they run out of nuclear fuel, and the energy that's been created in the inside the nuclear fusion suddenly stops, and there is a collapse and release of gravitational energy which hits up the outer shell, and makes it expand in the form of a supernova shockwave. This happens when this outer shell hits the expanding inner part of the core, and recoils out in a shockwave. And this shockwave carries the high mass elements formed in the interior of stars and distributes that in the universe, in the interstellar medium, from where new stars starts forming, new planetary systems starts forming, and then these new stars and new planetary systems are built with the material that is gathered from the death of these older stars. And be amazed when you see that the typical periodic table that you all know about, where does it come from? All the elements in the periodic table. Well, so the lighter mass elements like hydrogen and to some extent helium were produced during the Big Bang. Helium is also produced in stars like the sun. Um, Higher mass elements are produced in higher mass stars, larger stars, and they're distributed through the supernova explosions through the universe. And that is the origin of most of the elements in the periodic table. So they are born inside of stars. This is important for us to realize. And it is through the death of stars in this big supernova explosions that they're distributed in the universe. And then from there, they form planets, other planetary systems, and our life, our technologies are dependent on all these elements that you see in the periodic table, including the metals, the gases, the oxygen, the iodine that is part of our thyroid glands, that's in fact produced in supernova explosions. So essentially, when you hear this quote that we are made of star stuff, that is actually the truth. Okay, let's now come back to our star, the sun. So the sun is right now in a stable state where nuclear reactions converting hydrogen to helium is producing enough energy to balance the gravitational attraction. And this sequence is like the prime time or the main sequence of a star, in which sunlight stars live for billions of years. And it's amazing that this happens because evolution of life also takes a very long time. And it's this stability, this slow burning of nuclear matter inside of stars, and this very delicate balance between this outward pressure forces and the inward gravitational attraction that makes a star stable and allows it to give light for a very long period of time, also allows life to form and evolve and advanced life forms to happen. These conditions are extremely rare, and that is why till today we haven't found evidence of life in any other planet beyond planet Earth. Let's now get back to the sun. The sun is actually, in fact, much more active. It is not just something that gives you light. There are violent storms on the sun, which is known as solar flares, and you see a solar flare happening on the surface of the sun in this satellite observation from the Hinode satellite, which is a Japanese space mission. You see these flares are associated with these dark regions on the solar surface. These are strongly magnetic regions where the magnetic fields are roughly 1,000 to 10,000 times stronger than the Earth's magnetic field. These dark regions are known as sunspots. These storms, which can also sometimes give rise to coronal mass ejections or ejections of vast amounts of plasma from the outer part of the sun, can carry the energy equivalent of 1,000 billion atomic explosions happening at the same time. And they're the most energetic phenomena transient energetic phenomena known to occur in the solar system, and sometimes they can generate severe storms near Earth and in the Earth space environment, which are known as geomagnetic storms. Um, the sun's energy, the output of energy, is variable. This energy output, which was at some point in time known as a solar constant, is not really a constant. You would note that sometimes when there's this regions known as active regions or sunspots, the energy being radiated from the sun is higher. This is an observation of the sun put together over multiple days, and since the sun rotates, you see the rotation of the sun over multiple days. Um, this observation is in extreme ultraviolet. In fact, therefore, whenever there are these strong magnetic regions of the sun, you see uh, higher emissions in the extreme high energy bands of ultraviolet, extreme ultraviolet, and X-ray emissions from the sun, and these have impacts on the Earth's upper atmosphere and our technologies. For example, when we have strong solar storms, these high energy photons and the energetic particles that are generated in the sun can travel to Earth within about 8 minutes and impact our sensitive sensors of satellites. It can impact, and you see it's an impact on our detector here in this observation of a satellite. This is from the Soho-Lascaux satellite, which is from the European Space Agency. They can also be harmful for astronauts out on space. These high energy particles from solar storms and also in the solar wind can interact with the Earth's upper atmosphere. And this primarily happens in the polar regions because these charged particles, these are plasma from the sun and the solar wind, they can get trapped in the Earth's magnetic field lines and reach lower down into the, lower down in the Earth's atmosphere near the polar regions. And when they strike the atoms, they energize them, which go into higher energy states. And then when they come back to the ground state, they emit photons. And the color of these photons is related to the energy or color of the photons is related to the transition from the higher energy state to the lower energy state, the energy difference. And that produces light of different colors. And this produces these beautiful auroras, which are known as northern lights, or when it's in the south, they're known as aurora australis. And this produces this beautiful phenomena. And you would often see in social media these beautiful pictures being taken by people who are in high latitude countries. And these are also happening because of the interaction of solar winds and this changing environment in space with the Earth's upper atmosphere. Often these interactions are hazardous. In fact, this geomagnetic storms that are produced because of what we know as space weather on the changing environment in space because of this energetic solar particles can impact air traffic over polar routes. So when you fly from, for example, New Delhi to New York, you want to fly over the North Pole because the distance, at 2 points on a sphere is shortest when you go over a great circle. And the great circle typically in cities situated on the northern hemisphere is over the North Pole. However, the polar regions are also most susceptible to changing space weather conditions due to the variability of the sun. And therefore, often over the polar regions, flights were not happening for a long time. They used to avoid the poles. But since we have now managed to understand the sun's activity and generate space weather forecasts, the number of flights over the polar regions have increased, and that you see here in this little histogram over the inset here, where you see the number of flights over the polar regions has steadily increased over time. And this is primarily because of our ability to forecast space weather. So there is less risk involved. Whenever there is severe space weather, we can forecast that, and flights just avoid the polar routes. Earlier, they would not fly over the poles because they were not going to take the chance of getting caught up in a solar storm when they're over the poles, because that would make the sensors of the satellite of the aircrafts malfunction, which will be very bad and risky for the aircraft. They also disrupt high frequency communication um, um, between the the ground traffic control and pilots in aeroplanes. In fact, whenever there is severe space weather, there is disruption in communication networks between satellites and the Earth, ground stations at Earth. GPS navigational networks, which rely on global positioning satellites around the Earth, they get affected and positional errors or inaccuracies happen. Dish TV satellite broadcasts get disrupted when there is severe solar storms and geomagnetic storms due to space weather. Geomagnetic storms induce large voltages at ground levels also, and this again happens in high latitude countries, and we know that this can take down power grids. So oil pipelines and power grids in high latitude countries are susceptible to geomagnetic storms, which are related to changing space weather conditions. In fact, in 1989, a big solar storm induced geomagnetic variations, which took down the North American power grid in Quebec, Canada, and Montreal was out of power for 3 days due to this solar storm. What's the relationship between a changing sun and our climate is also a very important question to ask. This is an important question to ask more in today's time because we are now vulnerable to a rapidly changing climate. What you see here in this little inlet here is the variation in the number of sunspots with time. And what we know is that there is this little, not little, quite a long episode in fact, between 1645 and 1715, when sunspots observed on the solar surface completely disappeared. There are very few sunspots seen during this phase. This phase, which is known as the Maunder minimum of the sun, also coincided with the coolest period on Earth known over the last few centuries. This period, known as the Little Ice Age, is a time when rivers, many rivers in Europe, are known to have completely frozen over. And this is a painting by a Dutch painter, Henrik Averkamp, which shows a river near Amsterdam being completely frozen over and people skating over and walking over the river. This doesn't usually happen even today. Rivers in Netherlands and in UK, in Europe, doesn't really freeze like this. Okay, but during the Little Ice Age, it did, and people often make the connection between the reduced levels of solar activity and climate. So, is there a direct connection between the radiation that the sun gives up and the Earth's climate? Well, so if you look at the sunspot activity, what you see here in the bottom plot is the number of sunspots, the strongly magnetized spots on the solar surface. And we know when there are more spots, the sun is brighter. The emission from the sun is brighter than you see here, in fact, in this satellite observation. Whenever there are sunspots, there is strong emission associated with that. And when you measure the amount of emission from the sun just outside of Earth, this is what you get. You see that emission is also varying. And whenever there are largest number of spots, the emission is stronger. When the lower number of spots, the emission is weaker. Now, over a typical 11-year period, which is the period of the sunspot cycle, this variability is not very high. But over long time scales of thousands of years, the variability is strong enough that one thinks it can influence climate. In fact, the energy of the sun is the primary natural driver of climate systems and atmospheric dynamics of all planets, including that of Earth. Right? In fact, in about half an hour, the sun provides enough energy to sustain the whole annual needs of humanity. This is an important statement I want to repeat. In half an hour, the sun provides enough energy through its light to sustain the annual needs of all of humanity. If only we could harness that energy. And this is why research into solar cells making highly efficient solar cells is so important, because if you can harness energy from the sun, this is the cleanest, most efficient way of utilizing a natural source of energy without generating rapid greenhouse gases. This energy, of course, is not a constant, it is variable. And one can look at long-term temperature records, which is plotted here with time over the past roughly 1,000 years in blue, and also the sunspot record reconstructed by various techniques is plotted here in red. The background is uncertainties. Let's not worry about that. But you see here that in the past, in the pre-industrial era, when there was not much greenhouse gas emissions, there seems to be a connection between changing solar activity and the temperature record of the Earth. The problem is that you also find that the last couple of hundreds of years, in the post-industrial era, after the industrial revolution happened in the 1800s, and greenhouse emission rose rapidly, in that time, solar activity has also risen, and global temperature record has also risen. This naturally gives rise to the question whether it's the sun which is driving global climate change, or whether it's human activity which is driving global climate change. This is a very important question which scientists have looked at very seriously over a couple of decades, and the Intergovernmental Panel on Climate Change, the IPCC, has done very, very rigorous simulations and studies. The results of the studies is something that I want to highlight here. And this should be apparent when I explain this plot here on the left-hand side to everybody. What you see here is climate model simulations. The blue curve here is climate model simulations which utilized only variations in the solar energy output. The pink curve here are climate simulations which utilize changes not only on the solar energy output, but also the changes in the equivalent radiative forcing or energy input into the Earth system due to changes in the greenhouse gases. That's the pink curve. And the black curve is the actual observed record of the temperature anomaly, or the rise in the temperature over a certain standard average. And you see the observed record agrees with the climate physics-based simulations of climate, which incorporate not just the forcing from the sun or solar forcing, but also the changes due to the greenhouse gases. In fact, estimates now suggest that the greenhouse gas emissions contribute about 90%, or contribute dominantly to the climate change that we've experienced in the last 100 years or so. It is not the changing sun, it is our activity, human-made activity, and the greenhouse gases that is contributing to climate change. And you see here on the right-hand side plots of some different greenhouse gases and how rapidly they have increased in the last 100 years. And this rapid rise in greenhouse gases is the reason of this rapid change in climate or global warming that we see right now. And I wanted to leave you with that message. Okay, let's now come to the sun and what the activity of the sun implies or means for the continued sustenance of life, or even the origin of life in planets. So what you have to understand from what I have told you until now is that in the vicinity of planets, the most dynamic, the most changing phenomena is really the star around which these planets are orbiting. So there is changing radiation from the sun, there is changing energetic particle fluxes from the sun, which is due to the solar wind, this flow of plasma from the sun. And sometimes there are strong solar storms which can impact planetary atmospheres. In fact, what we know now from various scientific studies, which I will not go into the details of, is that this strong radiation from the sun can energize the atmosphere of planets. And if the planets lack magnetic fields, then these energized atoms in the outer atmosphere of planets uh, gets blown away by this flow of plasma from the sun, which is known as the solar wind, leading to the loss of planetary atmospheres. It's only possible to hold on to atmospheres if you have very strong gravity, which is possible for a massive planet, or if the activity levels of the star is very weak, or if the planet has a magnetic field. Now, the Earth has a magnetic field, and the Earth produces magnetic fields in a mechanism known as magnetohydrodynamic dynamo action, which produces a magnetosphere around Earth, which keeps away the energetic solar particles, the charged particles, from coming and impacting the Earth's atmosphere, and helps protects the Earth's atmosphere. This invisible magnetic field lines, known as the magnetosphere, is really important. And we see the importance of the magnetosphere by looking at another planet, Mars. Mars is often known as the twin of the Earth because many billions of years back, it's thought that Mars had an atmosphere which was, if not similar, but somewhat similar to that of Earth. Okay, so at about 1.5 billion years into the age of the solar system, or the age of planets, Mars is also thought to have had a liquid iron nickel core in its interior, and also this was strongly rotating. And this rotating core produced magnetic fields through certain inductive effects known as dynamo action, which follows from Maxwell's equations. And therefore, Mars had a strong enough global magnetosphere which could help protect its atmosphere. And at about 1.5 billion years, Mars also had a moist atmosphere with sustained greenhouse effect, which is thought to have been conducive for life. And this is why even today we are sending probes to Mars to search for any evidence of either past life or life buried in below the surface of Mars. However, the current Mars at 4.5 billion years of age does not have an atmosphere. And we often ask the question, why? How did it lose its atmosphere? Well, the clue is that right now Mars also has a solid core, not a liquid conducting core like what Earth has. That liquid iron nickel core that Mars had somehow froze over and became solid. And so there is no fluid motions possible, and this stops the generation of large-scale magnetic fields. And so Mars lost its protective magnetic fields of magnetosphere somewhere in between 1.5 billion years and now. And this led to the sun's activity and the solar wind coupling with the Earth's with the atmosphere of Mars and slowly eroding it away. It's like blown away with the wind. If I take some dust and blow into it, the dust will blow away. Similarly, over a long period of time, the sun's plasma winds coupled with the atmosphere of Mars energized it and slowly eroded it away. And right now, Mars has a very cool, very thin atmosphere, which is only rich in carbon dioxide and is thought to be only about 100 meters in thickness, and not conducive to life. So the loss of the magnetosphere of Mars has led it to be uninhabitable, with no possibility at least of surface life because of the loss of the Martian atmosphere. And this is intimately tied not only to the activity of the sun, it's also tied to the ability of the planet to host a magnetic field, which the Earth does, but Mars doesn't. And now you have another new surprise, which most of you are perhaps not aware of. The fact that you exist, the fact that I am being able to talk to you, we have this interaction today, is also related to the fact that there is dynamo action inside of Earth in the outer liquid iron core, which sustains the Earth's magnetic field or magnetosphere. If the magnetosphere was not there, life may not have been possible on Earth. Okay, how do we now explore the sun? How have we figured all of this out? How do we explore the sun? How do you know it's an active star? How do you know it's variable? Well, we can do it sitting on Earth through computational models. We build models inside computers to figure out how does the very hot, dense plasma system inside the sun behave. And we solve equations of magnetohydrodynamics inside computers to figure out how the sun produces these magnetic fields that we are observing here in a simulation, which is marked in different colors. And these magnetic fields emerge out in big loops, in this ring-like loops. They can emerge out and form sunspots, which you eventually see manifesting in the surface of the sun, which then produces this changing activity of the sun. In fact, we can forecast the future of solar activity. This is a forecast from our group at the Center for Excellence in Space Sciences India, which was published in Nature Communications a couple of years back. And you see that we have forecast how the activity of the sun would be in the next 10 years up to 2031. And we are now following solar activity very closely to figure out if our theoretical computational forecast agrees with what is the reality. We can also look at the sun's outer atmosphere through satellites and model them in the computer as well. What you see here, and this is amazing that the sun provides the sun's outer atmosphere, the only natural environment close by to actually see magnetic loops. What you are seeing are called coronal lobes in the super hot outer region of the sun's atmosphere known as the corona. And these are actually tracing out magnetic field lines. Much like if you have a bar magnet and you distribute some iron fillings around it and shake that piece of paper on which you've distributed the iron fillings on top of the bar magnet, they will follow this magnetic field lines. Similarly, this hot plasma traces out the magnetic fields in the sun's outer atmosphere. This outer atmosphere is super hot. The origin of this atmosphere is thought to be coupled to the existence of magnetic fields. And it is in this outer atmosphere of the sun, the corona, that magnetic storms, strong magnetic storms, are born. We can in fact also solve certain physical equations to understand the formation of the sun's corona, understand the distribution of magnetic fields in the sun's corona. And here you see some simulations from the computer using this magnetohydrodynamic models, again from our Center of Excellence in Space Sciences India at ISA Kolkata, where we matched the distribution of the corona's intensity with the simulations observed during the Great American Eclipse of 2017. And we usually wait for eclipse observations to see the sun's outer atmosphere, because the sun's disk is so bright that normal times, if you look at the sun, your eyes and the instruments, don't look at the sun directly ever because you'll go blind. But even if you look through instruments, the instruments get saturated by the very bright disk of the sun. Only when the moon covers up the sun's disk, the faint outer atmosphere or corona of the sun becomes visible. And therefore we wait for eclipses to test the computer simulations, to test our physical hypothesis with what is observed. In fact, eclipses have a long history of testing physical ideas. One of the most famous ones, I think, was 1919, when Einstein's theory of general relativity, the bending of light, also special relativity, was confirmed by an eclipse expedition led by Sir Arthur Eddington to Africa. Anyway, coming back to the sun and its corona, I don't know how many of you are aware, but the origin of the name coronavirus, which I'm just recovering from, in fact, is also the sun's corona. And it is because if you look at the sun's corona, it's structured in this loop-like structures, which is bright in certain regions which follow the magnetic fields of the sun. And if you look at a coronavirus, COVID molecule, a SARS-CoV-2 molecule, that has the spike proteins, which look like extended structures out of the surface of this virus. somewhat akin to the spike-like structures you see in the magnetic fields of the sun's corona. And that's where the name coronavirus comes from. So the sun's corona and the coronavirus have this common feature in the naming of it. And that's where, of course, the commonality ends. And this is a curious, intriguing fact that I wanted to tell you about, because this relates to what I study, to what is going on Earth right now. When you look at the sun's corona, this is where, and this is an actual observation from I think this is the TRACE satellite, which is a satellite of a joint mission really of NASA and ESA. And you see this outer coronal loops, the magnetic loops, sometimes becoming unstable and forming these solar flares or solar storms. These solar storms, in fact, sometimes when they're energetic, can throw out a large mass of plasma from the exterior of the sun's atmosphere. And these are known as coronal mass ejections. So ejections of a large amount of mass from the sun's corona, and therefore they're called coronal mass ejections. These coronal mass ejections, when they come and impact the Earth's magnetosphere, because they're carrying large amounts of magnetized plasma, they can change the Earth's field, the electromagnetic field, and produce geomagnetic storms. And these geomagnetic storms are the ones that can then take down communications, our high frequency communication systems. It can take down electric power grids. It can disrupt communications and also air traffic over polar routes. It can give rise to electric power grid failures. And this is very important to understand the interaction of these storms with the Earth's magnetosphere. So what you see here is another computer simulation, which we have developed. There are very few groups in the world with such capability, and we are very proud at CESI, the Center of Extensive Space Sciences in India, to be the only ones in India, and only one of less than 10 groups in the world with such capability to understand how the solar wind and solar magnetic storms impact the Earth's magnetosphere and produce perturbations in the Earth's magnetic field. And you see here the sort of solar wind, which is supersonic. It's traveling at the speed of, speeds larger than the speed of sound, impacting the Earth's magnetosphere atmosphere system and producing what is the steady state atmosphere and magnetosphere, where you see the magnetic field lines of the Earth being squeezed on the side facing the sun. And these squeezed magnetic field lines produce excess pressure, and this stops the magnetic fields and the plasma particles from the sun from entering closer to the Earth's atmosphere, thereby protecting it. So this closest part, the interior part of the atmosphere, is protected by the squeezed magnetic fields of the Earth, and therefore you see the importance of the Earth's magnetosphere in these simulations, in the protection of life. Well, we also explored the sun through multiple satellites because of its importance. And again, usually, India lags behind in following up what more advanced nations are doing. However, I must say that the Indian space program is trying to catch up pretty fast. So you see here multiple satellites by NASA, by the European Space Agency ESA, and some by the Japanese Space Agency JAXA up in space. There are more than 30 satellites which are looking at the sun and the influence of the sun on the near space environment or studying space weather. This is another way we measure the changing conditions. We observe the sun, we measure the changing conditions in space which impact Earth. And through this and our theoretical and computational models, we build a picture of how the sun is influencing Earth's atmosphere as well as the Earth's technology. India's first sun-observing mission, the Aditya L1 mission, will be sent out within the year. And this is our first solar observatory being built by ISRO and multiple different institutions around the country, including the Center of Excellence in Space Sciences at ISRO. So the Aditya L1 mission will be a comprehensive solar observatory which will look at the origin of the variations in solar ultraviolet radiation. It will look at the origin of solar magnetic storms or coronal mass ejections. It will look at the origin and variability of X-ray emission from the sun. It will also study the in situ plasma environment. By in situ, I mean the local plasma environment that's just outside of the Earth's atmosphere, sitting at what is known as Lagrange point L1. And this environment is flowing, it's not a static environment, it's flowing from the sun through the solar wind. The storms and winds are traveling from the sun through Lagrange point L1 before hitting Earth. And therefore, you may have a little bit of a window, like a half an hour window of advance warning of the environment in space that is going to influence the Earth's upper atmosphere. We're also planning a telescope which is going to be India's and probably Asia's largest solar telescope. It gets built in the next 5 years, which is going to be situated in Ladakh. This telescope is going to look at very high resolution the magnetic structures within and outside of sunspots, which are really the genesis or the origin of variability in the solar radiation, the changes in the solar radiation, and also which results in magnetic storms from the sun. And so we hope that the ability to look at very high resolution through this large solar telescope will help India and the world understand how the sun produces this activity which influences our life and our technologies. Finally, I want to end with a little bit of philosophical story of the end of our star, which is not based only on philosophy but real science. The philosophy bit is about what happens to us or humanity. You see, eventually, the sun will run out of hydrogen fuel. When every star is born with a finite amount of hydrogen fuel or other kinds of fuel that it can burn to counter the action of gravitational contraction, because gravity is always trying to contract. And the nuclear fusion is producing energy and high pressure and temperature, which is trying to build up a pressure gradient, which is acting against this tendency for the star to contract. The stable period will only last until there is hydrogen fuel within the sun. When it runs out of hydrogen, the nuclear fusion of hydrogen to helium will stop, and then suddenly there is no more nuclear fuel to hold the star in its main sequence stable form. And there will be a series of cascading effects, which will eventually lead to the outer part of the sun blowing out in a form which is known as the red giant star. The sun will end its life through a series of steps, first becoming a red giant. When it becomes a red giant, the outer part of the sun will expand and start eating up all the planets, the inner planets, including Earth. And this glowing outer shell will sort of slowly expand away and engulf the solar system. Eventually, this expanding outer part of the sun will form what is known as a planetary nebula. The inner core of the sun will collapse into a more or less dead star, which is known as a white dwarf. I call it a dead star because there is no nuclear fusion going on. So there is no real dynamic activity inside this dead star to emit the necessary photons or energy required to sustain life around it. And so essentially, the means of photosynthesis, the energy that sustains life, will be taken away from us. And this glowing outer shell will also envelop planets and make the solar system uninhabitable to life. So life as we know it will come to end in this sort of very beautiful way, because this planetary nebula is so beautiful. But then life is no longer possible in the solar system. That's the sad bit. So the question is, what happens to humanity as we know it when this occurs, when the sun as a star dies? Well, this is where the philosophy starts, in the sense that by the end of the death of a star, the sun, in about few billion years from now, if we have not managed to find another planetary system far away, where there is a stable star, where the conditions are stable, where we have the source of energy to sustain life as we know it today, will be gone. And if we are the first source of life in the universe, that is a terrible tragedy. If the other life forms somewhere else we do not know in the universe, after humanity on Earth comes to end, there will be life that is continuing. But if we are the source of life to eventually move through and habitate the universe, if we do not find a way out of Earth, of the solar system, then life will end. Now, do you think it's impossible to find another habitable planet beyond the solar system? This is where the question becomes a bit of a philosophy. But then think of the last roughly 50 to 60 years, where from not having rockets to move out of the Earth, to having gone to the moon, to having gone to Mars, we have satellites which have left the solar system behind. The Voyager 1 or 2 spacecrafts, right? Voyager 1 and Voyager 2, which have now flown away beyond the solar system and is somewhere deep in outer space. 50 years. Give us a billion years and we do not know what is possible. Maybe we'll find another place beyond Earth. I do not know how many of you recognize this image, which I find to be quite profound. This image is of a double sunset in another planet, which is fictional. This is a fictional story of Star Wars. This is Star Wars 4, A New Hope, where Luke Skywalker has returned and is walking towards this double sunset, this two-star system, around which the planet Tatooine orbits. And the question I would like to leave you with is this, that perhaps if we are able to challenge ourselves to build the technology that it takes to leave Earth and go beyond the solar system, we may have yet hope to sustain life as we know it, our progenitors, our seeds, when the sun and the solar system are gone, because we have perhaps found another system, just like what exists today only in science fiction. And therein lies the importance of exploring beyond Earth, of exploring beyond the boundaries that is natural to us and going beyond it, fighting what is given to us and going beyond it through the resources that have been given to us, to ensure that we may be able to find another planetary system that can host life some millions of years from now. So this is my last slide, where I want to leave you with the story that I've told you, the highlights of the story. So our star, the sun, is actually an ordinary star. It's not a hyperactive, not a supermassive star. It's not a black hole. But because it's ordinary, because it's so stable, it makes life possible around it. We owe our life to our sun. In fact, we also owe our life to more massive stars, which have died and in their death have produced elements which have come and found their way to planet Earth, which has found their way into our bodies. So understanding this intimate relationship that exists between life, between planet Earth and the sun and other stars, helps us understand the ecosystem, the astrophysical ecosystem that we live in. It helps us explore other extraplanetary systems in search of habitability beyond the solar system, which may not be a question that confronts you tomorrow or day after tomorrow, but this is a question that is going to confront humanity in the future. And unless we start to answer some of the profound questions, the profound challenges that are required to be overcome, to be able to go beyond Earth today, we will not be able to survive in a changing solar system tomorrow. So there are many things that we do not know about the vast cosmos we live in. There are many things we know that tells us that we must find another home as well beyond Earth. And I hope that some of you would be able to rise up to the challenge, and many of you would be answering some of these questions that will eventually allow humanity to be sustained well beyond the death of the sun and the solar system. Thank you for listening to me, and I'm happy to take any questions.
Thank you, Dibyendu, for a nice talk. And now question and answer session. So first I'll take the question offline if there is any. So any question? Yeah, speak up.
First of all, I would like to thank Dr. Nandi for such a wonderful.
I can't hear the questions. Maybe Rakesh, you have to repeat it because you're
Maybe
speaking
you
to the
can
mic.
come here. Possible? Yeah, we are bringing him here.
Good evening, sir. First of all, I would like to thank you for the wonderful presentation by making it such a wonderful story backed by scientific evidence. Sir, my question were that if you could define interstellar medium in simple terms, and why is it that in such extreme conditions of the interstellar medium we find such a richness of molecules in there? And my second question was, as you mentioned, that the Mars, due to the absence of magnetic field around the Mars at the moment, the atmosphere has gone thin. So why is the reason of the dense atmosphere on Venus? Is it just magnetic field or other reason?
Okay, so those are very interesting questions. Particularly the second one, because the second one is actually a very technical question, but this is a question that we're trying to find the answers to right now. Let me first answer the first question. So what is the interstellar medium? The interstellar medium, in very simple terms, is extremely low density, in other words, very thin distribution of gas that exists between clumps of matter like stars or planets. Now, this interstellar medium is also full of essential elements and perhaps molecules which are essential for life. And how did they come to be? It came to be because remember that the first stars, which were born about 1 million years into the age of the universe, also died, went through their life cycle and died about 10 million years into their lifetime. And after their death, the more massive stars die in these big explosions known as supernova explosions. The elements in this cooked in the inside of the stars are spread through the supernova explosions, which travel very large distances. Perhaps also through extragalactic jets, they're mixed up in the intergalactic and interstellar medium. And so therefore this high mass elements make their way into the interstellar medium. From there, when you start clumping matter again together to form new stars and new planets, you now have some of those elements and molecules that were created elsewhere forming the basis of life. So it is believed that life may not have been possible around the first generation stars, life as we know it today, but it has only been possible in the second generation stars and planets which have formed after the date of the first stars. I hope that answers your first question. The second question, which is a very interesting question, is why is it that Venus has an atmosphere, but Mars doesn't? Well, so Mars doesn't, because Mars lost its magnetic field, and the erosion of the atmosphere due to the impact of the solar wind around Mars slowly took away the atmosphere of Mars. Now, Venus is very similar, and this is what triggers your question. Venus is very similar to Mars in the sense that Venus also does not have an intrinsic magnetosphere. So Venus, in fact, has a very thick atmosphere of gas around it. It doesn't have an intrinsic magnetosphere but what it has is an imposed magnetosphere. The imposed magnetosphere is because of the solar wind magnetic field lines draping around the planet Venus. Now, the planet Venus is also losing mass. It's losing its outer atmosphere because it's not protected. But its inner atmosphere, which is thick and which is protected by an imposed magnetosphere, is not being lost. So the rate of loss of the Venusian atmosphere is an open question. And right now, we are actually planning to send satellites to Venus. We are planning to do simulations of Venus to understand why is it that the planet Venus has managed to hold on to a thick atmosphere around it, even at this point in time. Is it because it's lost its magnetosphere much later than Mars? This is an open question, and we do not know the answer to that question. Now, having said that, let me make it very clear that the Venusian atmosphere is not conducive to life. It has immensely high density, so which implies that the pressure is very strong, not very good for life. It is rich in something called phosphine, which is poisonous to life as we know it. It's very hot and warm. So it's not believed that life is possible in the Venusian atmosphere.
Okay, sir. Thank you very much.
Yeah.
And in fact, let me add that there is consideration of a mission to Venus by ISRO. There's a proposal for it.
Sure, sir.
Any other offline question? Anybody? Yes. So then I'll go to online question from YouTube. Mr. Gautam Shil is asking, can you please explain Lagrange points?
Okay, yeah. The Lagrange point L1, there are a couple of Lagrange points. The Lagrange point L2, L3, L4, L5. Let me focus on L2 Lagrange point is where JWST is, the James Webb Space Telescope, because it's behind Earth, from where the sun is pretty much almost permanently eclipsed. Because for JWST, the James Webb Space Telescope, which is looking at very distant objects, very faint objects, the sun is a problem because it's too bright. So it's just behind Earth all the time in Lagrange point L2, where it's in stable orbit. The sun and the Earth's gravity has cancelled. Similarly, at L1, Lagrange point L1, which is on a line connecting the sun and the Earth, but very close to Earth. Again, this is a point where the gravitational attraction of the sun and the Earth and the satellite are such that there is cancellation of this gravitational attraction, and there is no gradient in the potential of gravity, and so it's a stable place where if you place a satellite, it will tend to be there. It will not tend to divert or move away from that point. You would need minimum fuel to keep the satellite in that location. And the beauty of that point, Lagrange point L1, is as the Earth rotates around the sun, that point and any satellite placed there is also moving along with the Earth around the sun. So Lagrange point L1 is a preferred location for observing the sun because it is observing the sun 24/7 without really going behind Earth and the sun being eclipsed at any point in time. It is also close to Earth, so it can continuously provide telemetry to Earth. So you can observe the sun 24/7 and you can downlink the data 24/7 if you have appropriate ground stations distributed across the Earth. And so this is a preferred location for observing the sun. And that is why the Aditya L1 mission, which you see here, in fact, the Aditya L1 satellite, is going to be placed at the L1, Lagrange point L1, close to Earth and along the Sun-Earth line, from where it's going to continuously view the sun.
Yeah, so now there is a question from press. So it's from the Telegraph in Schools, TTIS. Maybe Averi is already there in GMeet. So, yeah, so can you ask the question?
Yes, sir. Good afternoon, sir. I am Aditya Banerjee from the Telegraph and Schools. We are a newspaper for the students. So my first question would be,
First of all, I can't see you, but that's okay. But can you come a little close to the microphone so that I can hear you? That's important.
yes, sir. Is this better?
Much better.
Yeah, come a little bit closer, I think, to the microphone. Let me see if I can manage to see the room. I'm not being able to see the room. Okay, now I see the room. Go ahead.
Is this better now?
Yeah.
Okay, sir. So my first question would, uh,
Hello.
so my first question would be, how was your experience being part of this program?
Which program?
So this one, the one organized by BITM just now.
Okay, so I mean, first of all, I would have been, of course, much happier if I could be physically there, so that I could interact with you all, um, and get to know, each of you, what your interests are, in terms of astronomy, how you are thinking of using astronomy, in your schools and colleges, of utilizing the expertise available at BITM or in our institutes to help you. Um, so I wish I could have started the dialogue physically there, but then I'm here virtually. You have my email. You have contacts of Rakesh, who knows me personally, because he graduated from the PhD program at SESI, the institute I lead. Um, so for me, this occasion is just the beginning. It is an occasion of strong potential to lead to something exciting in the city of Kolkata, where I hope that the schools and the colleges will come together along with us, the experts, who have some knowledge about astronomy, um, and where we can all work together to bring home the excitement of astronomy and the astrophysical sciences, and in principle the sciences, all kinds of sciences, to the schools and colleges in Kolkata. So I think today is a mere introduction to the possibility. Uh, Unless we utilize and build upon it, it will just remain another online lecture. And I hope that it will not be the case. So while I am extremely happy to be able to talk to all of you and to reach out to a much larger audience than what I could have in my own institute, to the city of Kolkata through you, I hope that you will also keep alive this interaction along with BITM and us, so that we can all work together to do something bigger than what each of us individuals can achieve.
Yes, sir. Sir, what first attracted you to astronomy and space sciences?
I'm sorry, I couldn't really hear your question. If you can just repeat it.
Yes, sir. What first attracted you to astronomy and space sciences?
Yeah, this is a normal question that's asked often, and you know, I think I ended up doing astrophysics by accident. I wanted to do sciences, and I due to when I studied in Kashmir English School, that was where my schooling was. Then St James School, and St Xavier's College. That's where I did my BSc. And then I moved to Indian Science, Bangalore, for my master's and PhD. Until class 12, I was not sure what I am going to become. I mean, in fact, I studied chemistry in presidency for 1 month and didn't really like. I mean, well, yeah, I thought chemistry is not for me. So I left presidency, and eventually I ended up through a long circuitous route through Vidyasagar College, finally to St. Xavier's College of Physics, where finally I thought that I found what I wanted to do, which is physics, not necessarily astrophysics. It's only when I went to ISC and started discussing about various science topics with various people. Eventually, I realized that astrophysics, the application of the knowledge of physics in understanding your universe, is what I wanted to do. So I think this was a work in progress. It was not like I looked up at the night sky one day and I was inspired to become an astronomer. And I think I would like to point out that it's perfectly normal to be confused, to not know what you want to be in life until a very late stage. And sometimes what you become is a result of some happy accidents. And that is fine.
Thank you, sir. What is your favorite aspect of your job? Please, could you share an anecdote?
There's a lot of feedback. Can you ask the question again?
What is your favorite aspect of your job? Something you enjoy or something you're really proud of in your line of work?
What is the favorite aspect of my job? Is that what you're asking, my profession?
Yes, sir.
Okay, the most favorite aspect, couple of things. Well, the most favorite aspect is nobody tells me what to do. I define my own direction of research. And in other words, I define my professional future. What am I going to do in my future? And as long as I am doing something which is generating new knowledge for the sciences, in general, I am left alone to do what I want. Now, of course, if I want big funding, if I want something bigger than my own science, want to build large groups, if I want to build a center, then I need to be doing something which is deemed useful by your society. Because eventually, all of you, the society sponsors our work, right? I am paid by taxpayers' money. The funding that funds my research is the money that comes from most of you, the public, who are paying taxes. And that is important. So it's important for the public to ask questions of why am I doing what I am doing and how does this benefit you? And so therefore, when I seek something which is beyond my immediate salary, some bigger grants, we generally want to do something that is of direct benefit to humanity. And therein lies the importance of application-oriented research, where we try to learn something from my free-spirited fundamental inquiry and transform that into applied sciences. And what I do there is in predicting space weather. So I try to use the fundamental knowledge that I've gained from my free-spirited inquiry defined by my own interests, and eventually applying that to understand how does the environment around planets vary? How does this variation impact satellites? Some 30 years back, nobody would have bothered about this, and people would have thought, okay, this person is just doing this because he's interested in this. But today we suddenly realize the importance of the space environment, space weather for the satellites, for defense communications, for communication technologies, for air traffic. And this is how fundamental research goes. We usually define a problem that we're interested in without knowing if this problem will suddenly become relevant in the future. And out of a million problems that many scientists are pursuing, even if 100 or a couple of hundred problems suddenly become relevant either in terms of knowledge or in terms of technology for the society, that is what is helpful. So this is very interesting that this individual, what I started from answering a question, what do you like most about my job? That I like the freedom to define my own choice. And that might mean I can go off in a completely tangential direction, which is useless. Often people deem useless for society because it's defined only by my own interest. Can in fact has the possibility of becoming very important many 100 years down the line. This is a message I also want to leave you behind with. that fundamental inquiry that is based on an individual interest may sometimes become very relevant. Then that onus is on us to recognize that opportunity and transform that knowledge to something that is of, actually of use to the society. Semiconductors, which was realized in AT&T Bell Labs many decades back from purely fundamental interest of a scientist, is something that powers our cell phones today. It powers the laptops that I'm talking through, and is ubiquitous in the technologies that we use, right? Well, so that was one of the great things I enjoy about science, is this ability for us to define our own direction of research. Second thing is time. I can keep my own time as long as I'm producing and doing my own work. Nobody can tell me that you have to work from this particular time to this particular time. So I can pursue my own interests in my own time. Although you tend to get very, very busy with more and more responsibilities, you have the option of not taking up those responsibilities. You have the option to define how you work, when you work, where you work. In most cases, at least in institutions which have the foresight to give you that independence of thought and the freedom to work on your own. Because I think the best science really comes out when you are left free to imagine.
Thank you, sir. In your opinion, how advanced is India when it comes to space sciences?
So it's a double-edged sword. In many ways, I feel that often as a country, we tend to follow others in technology and in science. And I don't need to really talk about it. It's in evidence, I think. I think most people tend to follow than actually lead, which is one of the issues with Indian science. I also find that often too many rules, too many regulations ties down creativity, and people tend to put restrictions and more friction in the way of ambitious people in India. Culturally, we are like that. We are intolerant of people who are different, who are ambitious, who have new ideas. And science and technology is all about ambitious people coming up with new ideas, who are breaking the old knowledge systems. I think we are a bit slow to realize that still, and therefore the obstacles we put in the way of science is more than in many Western countries. Having said that, if you look at where do we stand as a country in terms of our GDP and things like that, in the last couple of decades, I think we have made important strides in science, and this is primarily due to the investment in science that has happened over the last 40-50 years post independence, and the realization that a modern self-reliant nation requires to be self-reliant in technology. We cannot always depend on other countries, right? I mean, the science we do is not really confined to borders. It's knowledge we create for everybody. But often technology is confined to borders, because while knowledge is shared in a very inclusive manner, I don't own the ideas that I give out. After my idea is out, it is owned by everybody. Anybody can use it. Often technological companies, the IP, the intellectual property regime doesn't work like that. So one has to develop your own technology. And in this, of course, I think we are making very important progress in the last few decades in space sciences. And given the size of our economy, I think the impact of the Indian space science program has been quite disproportionately large. And we can always criticize and say we should be doing much better. We could indeed be doing much better. The systems can be much more creative. Systems could be much more open. But still, in spite of all those hurdles that we still have, I think the Indian space science program has made remarkable contributions, remarkable technological progress. And I think to a large extent, this was driven by the sanctions imposed upon India once upon a time by many of the Western nations, which forced us to develop our own technologies in rocket science, which has propelled India's growth. And this is a lesson that sometimes it might be useful for us to go our own way in certain dimensions of science and technology, particularly in those dimensions of science and technology which are not very easily shared across borders.
Yes, sir. You're acquainted with not just the Indian Institute, but also foreign centers of research. In light of that, what changes would you like to see in this field of study in India?
Well, I think you got some aspects of my answer to that question from my criticism of the Indian system, right?
Yes, sir.
As I said, I mean, and you were in school, right? Or you're in college?
Sir, I'm in school, class
You were
11.
in school, right? If you're in a typical school, which board are you in? CBSE, ICSE?
I see.
ISC, that's right. Okay, whatever, right? In a typical school, you're in a class. You have some knowledge that is written down in books. The primary role of teachers in this country is to deliver the knowledge that is already in books to you and try to make sense of it, right? Now, if there is one of you in class who has read something somewhere which challenges that knowledge, you raise your hands and stand up and say, but I have just read that new research says that what is written in the book is not right, and this is what it is. I think 90 out of 100 times your teacher will think that you are just being a nuisance in class, right? Now, you can extrapolate that and imagine then that, or let me say that you are a boy and you walk into a class with a ponytail, right? One day. Or you are a girl and you walk into class with a dress that is not part of the code of conduct of your school. Our culture and our society is such that you will be branded a problem maker, right? Now, if you extrapolate that to science, that doesn't work. And culturally, we are like that. Culturally, we have a lot of inertia. We tend to believe that the certain systems we must always follow, right? In science, we're trying to break those systems all the time because science depends on the breakdown of past knowledge and the creation of new knowledge. This is where I think some of our past holds us back, because often I find that new ideas, new creative ideas, ambitious people in science who are trying to break the system come up with against a wall. They hit a wall. The system tries to hold them back. The system tries to change new people who are assimilated from outside back into the country before they can change the existing system within our institutions. And this, I think, is one of the things that holds back Indian science. I think there has to be much more disruptive creative freedom within Indian institutions, including in schools and colleges. Teaching has to be disrupted in a way that we value creativity, understanding over knowledge. Knowledge is in my laptop, knowledge is here, right? My brain should not be taxed with retention of knowledge. I should be allowed to use everything that I can in today's modern world to retrieve information and knowledge and utilize it creatively. That is where our onus should be as a society. We should be a creativity-driven society rather than an information retrieval, knowledge retrieval-driven society. I'm sorry if that was a little bit too dense, but I feel very strongly about it.
No,
And I
sir.
hope that this is something that I could, that you
So-
appreciate a little bit at least of what I was trying to talk about.
Yes, sir. What should one do, or what mindset should one have to pursue astronomy, astrophysics, or space sciences?
astronomy and astrophysics is a very different kind of science, in the sense that it might, I mean, if you study the sun and the space in a space environment, yes, it has some immediate applications. But as I said, a couple of decades back, nobody thought that there'll be there would be these applications, right? But today we know that we are so seriously dependent on space-based technologies and satellite systems that we have to worry about space weather. But there is a lot of astronomy and astrophysics which worries about more distant objects, about black holes, about galaxies, about stars, which doesn't necessarily immediately impact you, right? So to be interested in that, to be interested in things that seem far-fetched, that seem very far away, you need to have a sort of a breadth of mind and acceptance of the fact that sometimes you create knowledge just for the sake of creation of new knowledge, not for the sake of immediate application. So astrophysicists and astronomers, are somewhat different people. They're somewhat mad, they're somewhat crazy. They kind of live in a domain where sometimes they don't worry about the big hole, the big crater right in front of their feet, which they might fall into, but they're more worried about the stars. And in a way, I think that makes astronomers also happy people. I feel they tend to have a larger, more broader interpretation of life around them, which allows them to look beyond small petty problems that confront humanity. We can be in the gutter, but we still see the beauty of the stars. And you need a certain bent, certain poetic, certain philosopher's bent of mind to be a person like that. So I think, when the people like in biology, for example, the ecologists, the evolutionary biologists, who look at large species systems, right? Large scale systems, they're somewhat similar. We're interested in the interconnectedness of things, in the broad connectedness of the universe to us, to our life. And that drives those bigger questions which are not immediately perhaps of any relevance, seem to appeal to us. So we are a different bunch of people. You can think of us as being poets of the scientific world.
Sir, how has astrophysics or astronomy or the space sciences been affected by the last few years of the COVID pandemic?
Well, space science has certainly been affected because what has happened, astrophysics, or the pursuit of astrophysics and astronomy as a sciences within institutions, as a field of research, is just as affected as any branch of science, right? Because of closures of institutes, because of physical distancing, students have been kept away from labs. But that is an impact that has been felt equally by all practicing scientists. But where there has been a bigger impact to space science and astronomers is the ability to go to your telescopes, the ability to build instruments in the specialized laboratories. Those extended lab closures have certainly put back a lot of ISRO space science programs. It has put back our involvement in building instruments to fly on ISRO satellites. It has impacted astronomers who have to go to telescopes physically and observe, on clear nights, the night skies. So that has certainly put back those people who work hands-on with either telescopes or with building satellites. Those programs have certainly been impacted in terms of facing long delays. Also, in terms of students in astronomy and astrophysics, as well as all other sciences, there has been an impact in terms of isolation. Science is all about interaction. It's about feeding your ideas of each other. And this long isolation, breaks from the institutions, has not been good for the mental health. And also, I think it has impacted fellowships because fellowships have finite tenure, but these tenures have been extended because of the COVID pandemic, and unfortunately, many people have gone without fellowship. And this, I think, is a terrible tragedy that has befallen students of science in the past couple of years.
Sir, just the last
Okay,
question.
sorry to interfere. So there are a lot of online as well as offline question is waiting as well for Dibyendu. So one question from Avijit Ghosh from YouTube: does any planet other than Earth have magnetosphere?
Well, yes, Jupiter has a magnetosphere. Jupiter has the strongest magnetosphere in the solar system.
And then
Now, the other thing is, you can ask this very interesting question: what about exoplanets? Well, beyond the solar system, we don't yet have any evidence because it's very, very difficult to detect magnetospheres beyond the solar system.
And then the next question from Rachita Ghosh from YouTube again. Sir, could you please explain brief about the black hole?
Okay, so the black hole is the end state of a very massive star, a typical normal black hole, not a supermassive black hole which is accreting matter, but a normal black hole which forms out of a very massive star which exceeds the Chandrasekhar mass limit. There can be various end states. It could be either a neutron star or it could be a black hole. Typically, a black hole is formed when the matter inside the star is so much that that even the degeneracy pressure of neutrons cannot hold the star together. It further collapses to form a black hole. And the black hole is essentially again a dead star, essentially, which has an event horizon around it. So, if you're within the event horizon, there's no information that can go from the black hole to the outside as the standard understanding of black holes. Typically, black holes are detected by not any information coming from inside the event horizon, but typically from infalling matter from around it called accretion disks, which when they get close to the event horizon, they become hot and they radiate, and also from jets. Where this black hole jets which eject material out, which can be detected in X-rays, which are used to detect black holes. Direct imaging is not really possible, except that very recently there of course has been this Event Horizon Telescope, which is really detecting more the shadow of the black hole and looking at the emission from the plasma around the black hole and seeing this dark shadow inside, by which is imaging indirectly the black hole. So that's a black hole for you. Yeah, it's the exotic end state of a star. Sometimes it can get supermassive by accreting more and more material and eating up other stars, and this keep on growing in size to become huge. And this happens to black holes in the center of galaxies, typically.
Yeah, so I'll take the last question since the audience is getting impatient for seeing the BITM facilities like telescope and Taramandal. So this question is from my colleague, curator NCSM CRT headquarters, Shaman.
Sir, I have a small question. If you see in all the images, the universe is shown as 2D. It's all planets will be revolving in the same plane. But as you said, the universe is made from an explosion. So during an explosion, the matter will go in all the sides. So how come this anomaly come to happen? I just had this question.
Okay, so that's a very interesting question. Essentially, what you are asking is, so let's say I have interstellar gas, out of which I collapse this into a star and a disk of planets around it. Why is it that I see revolution? Why is it I see rotation? Right?
Revolution is okay, sir, but it's all in same plane. Like if you see all the motion of
it's not in the same plane. No, it's not. Usually galaxies tend to be around a plane or planets seem to be around a plane, but that can be explained based on how matter accretes onto a spinning object, around the spinning object. But the universe is not a plane. The universe is a three-dimensional object. It's certainly not a plane. Matter is not distributed in the universe in a plane.
So, yeah, but if you see, like there are no planets.
The universe is isotropic on all sides. Doesn't matter whichever side of the universe you're looking into, it looks isotropic. So which implies the distribution of matter in the universe is uniform. Very small scales. Now, by very small scales, I mean scales of planetary systems, or maybe sometimes galaxies. You see distribution of matter on the edges in spiral galaxies. But overall, the universe is at large scales fairly uniform.
Thank you.
Yeah, so with this last question, let's conclude the online inauguration. There will be another part which will be offline, seeing the facility, but this is just, as Dibyendu correctly pointed out, just the beginning. So we'll be looking in future for your presence in offline mode. So get well soon. You are already recovering, you told, and best wishes from us. And that's all from our side for today.
Well, thank you very much, Rakesh. Thank you very much to BITM for hosting me, and I am happy to be part of your inauguration, and wish you all the best.
Thank you. So see you soon. Good night.
See you. Good night.